Hello everyone, and welcome to today's technology webinar, a perfect match pairing gate drivers to EliteSiC, brought to you by onsemi. This webinar provides guidance for pairing gate drivers to silicon carbide MOSFETs for applications including uninterruptible power supply, energy storage systems, and solar and electric vehicle charging. We will explore how to reduce conduction and power losses to maximize efficiency of voltage and current flow during SiC turn on and turn off, and we'll also discuss the relationship between gate drive current and the SiC MOSFET gate to source voltage and the total gate charge. I'm Kylie Miller with onsemi, and I'll be your moderator today. At the end of the webinar, we'll be holding a Q&A session to answer any questions you may have. During the webinar, you can type your questions into the chat box on your right, and we will answer them at the end of the webinar. I will also share the slide deck of the webinar with you during the Q&A session. This webinar will be recorded and posted at onsemi.com, and you'll be notified via email when the recording is available. Now, let's meet today's presenters. Bob Card works at onsemi as a marketing manager and is in the analog and mixed signal group. Bob Card has over 30 years of experience in the semiconductor industry, tackling applications and technologies including brushless motor control, Li-ion battery management and charging, wired and wireless communications, and gate drivers. A true expert in his field. Bob has 12 U.S. patents and multiple publications and blogs. Now, let's get started with the webinar.
When you look at the high-power megatrend applications in today's world, like solar, EV charging, HEV and EV traction inverters, onboard chargers, motor drive, high voltage DC to DC and HEV or EV, as well as networking, servers, and power supplies, the power can range from 10 kilowatt to roughly 5 megawatt, which is a pretty big range of power. And so when you look closer at these electronic topologies or block diagrams that make up these high power megatrend applications, like for example the three-phase brushless DC motor at the center of your screen, or at the top right of your screen a solar inverter using an H-bridge topology to deliver AC power to the grid after harvesting DC power from the sun, or below that where the uninterruptible power supply comprised of many lithium-ion cells in parallel and series also uses an H-bridge to deliver AC power to the grid. And then finally at the bottom you will find the classic switch mode power supply topology converting AC power on the left to DC power on the right. You can clearly see the elephant in the room for all of these high power megatrend applications, and that is the gate drivers and the switches. And the switches are typically either silicon, IGBT, silicon carbide, or GaN. This slide captures the general sweet spots for your switch selection for these high power megatrend applications. The x-axis captures the pulse width modulation switching frequencies in hertz, while the y-axis captures power in watts. You see how IGBTs are a preferred solution over silicon for high power, but more importantly, characterized by the horizontal red lines going left to right, you can also see how many of these applications are transitioning from IGBTs to silicon carbide above roughly 10 kilowatt and below roughly 10 kilowatt from silicon to GaN or gallium nitride. And that's because for many of these applications, when switching faster, the physical size of your passives, like transformers, capacitors, and inductors, can be greatly reduced for the same amount of power. So by switching faster, you can achieve higher power density, and that's a good thing. Silicon carbide and GaN technology, also known as wide bandgap, is a superior solution for switching faster and achieving very high efficiencies for these high power megatrend applications. I'm old enough to remember if I designed a 100-watt power product achieving 95% efficiency, I can call it a day. And that's because managing 5 watts of power dissipation is really not rocket science. It's relatively straightforward. But now when you're talking about power applications in the hundreds of kilowatts, if not megawatts, managing power dissipation in the kilowatts or tens of kilowatts becomes a significant design effort on its own. In short, how do you cool that thing down? So the point is, we used to say every % of efficiency matters. But now we have to say every milli% of efficiency matters. The total power loss can be approximated as the sum of the conduction losses plus the switching losses, where the conduction losses are a function of Ohm's law, or I squared R, where R equals the MOSFET's drain to source resistance, or RDS on, when fully turned on, and I equals the drain current flowing through the MOSFET. Meanwhile, the switching losses, a bit more complicated, include such parameters as QG, or total gate charge, QRR, or reverse recovery charge, CISS, or input capacitance, RG, or gate resistance, and your E-on and E-off losses, to name a few. In most of these high-power megatrend applications, there is an MCU that needs to turn these switches on and off. But the I/O buses of contemporary MCUs are limited to 1.8 or 3.3 volts due to their small process node processes. So MCUs need a gate driver to provide enough voltage to fully turn on and off these switches. But each switch type has a different voltage requirement for that gate drive voltage. For example, silicon typically needs a 10-volt swing from 0 to 10 volts. IGBTs typically 0 volts to 15 volts. And silicon carbide typically needs a 21-volt swing from -3 volts to 18 volts. Of course, you always want to check with your switch data sheets for the exact requirement for turning your switch on and off. This is just a general first-order approximation. So when driving silicon carbide by onsemi or EliteSiC, it's fine to swing it from 0 to 15 volts. That will work. That is a fully functional situation. However, if you go from 0 volts to 18 volts, you'll get better efficiency. You'll reduce your conduction losses by 25%. You reduce your E-on losses by 25%, and you reduce your E-off losses by 3%. And then if you go the full gambit and go down to -3 to 18 volts, that's your best efficiency. There, you reduce your E-on losses by 3%, and more importantly, you reduce your E-off losses by 25%. This slide captures more detail with respect to the efficiency improvement during turnoff when using onsemi's EliteSiC Gen 2 1200 volt M3S series 22 milliohm silicon carbide MOSFET. This plot, which comes from onsemi's apps note AND 9024, which I highly recommend if you wish to learn more about onsemi's M3S EliteSiC, captures the negative gate bias voltage on the x-axis and switching losses in microjoules on the y-axis. You can see by the plot that approximately 100 microjoules of E-off losses can be saved by switching off down at -3 volts versus 0 volts. So one can clearly see the efficiency benefits of negative voltage bias during turnoff. Another benefit not captured in this plot is mitigating against accidental turn-on during intended turn-off. The high gate drive current during turnoff can interact with the MOSFET capacitance at the gate as well as package and PCB trace inductances, resulting in excessive ringing during turnoff. This ringing could accidentally trip the gate to source voltage threshold, momentarily turning the SiC MOSFET on during intended turnoff. This is a bad thing. So switching off down to -3 volts, if ringing does occur, provides an additional 3-volt headroom from tripping the gate to source voltage threshold due to that ringing. Now let's take a closer look at the turn-on of a MOSFET or a silicon carbide MOSFET. At the top right, we have a schematic block diagram of a gate driver on the left, driving the SiC MOSFET on the right, separated by an external gate resistor named R-gate. The green arrows capture the current flow. From top to bottom, the SiC MOSFET's drain pin, gate pin, and source pins are clearly captured. The gate driver is responsible for driving the gate to source voltage, or VGS, to its maximum level, allowing the drain current, or ID, to flow from drain to source with the minimal internal resistance, or RDS on, of the SiC MOSFET. You will also note the gate to source capacitance, or CGS, the gate to drain capacitance, or CGD, and the drain to source capacitance, or CDC, in parallel with the body diode. Both the CGS and the CGD need to be fully charged during turn-on. And this is one of the main reasons why so much current is required out of the gate driver to fully turn on. So now let's break down the turn-on sequence of events into 4 distinct time states. So for T1, the gate driver output rises to the VTH, or the on-state gate threshold voltage of the silicon MOSFET. The actual VTH of each silicon MOSFET can vary depending on the device and temperature, and can be found in the respective datasheet. During T1, the gate driver exhibits its peak source current, or IG, and no change to the VDS, or the ID. During time state 2, now the gate driver output voltage climbs to the Miller plateau of the silicon carbide MOSFET. The IG decreases in a linear fashion, and the ID now fully conducts. During time state 3, the gate driver continues driving through the Miller plateau of the silicon carbide MOSFET, where the IG also plateaus, but notice the VDS is now discharged. And with time state 4, the gate driver reaches its maximum output voltage, or VGS. And now the silicon carbide MOSFET is fully enhanced, exhibiting a minimum RDS on versus the ID flowing through it, and the IG is very low. And now we can examine the SiC MOSFET turn-off in 4 distinct time states. At time state 1, the gate driver decreases the VGS from a maximum voltage to the Miller plateau. This triggers a transient peak IG sink current, which then decreases in a linear fashion until reaching the Miller plateau, with no changes to the VDS or ID. At time state 2, the gate driver continues sinking current through the Miller plateau. The VDS is now charged from low to high to the max voltage, and the drain current, or ID, is still flowing. At time state 3, the gate driver reaches the VTH, or turn-off threshold, of the silicon carbide MOSFET, and the IG sink current falls in a linear fashion. Now the ID falls to 0. And finally, at time state 4, the gate driver is either at 0 volts or below 0 volts. The IG is 0, ID is 0, and the SiC MOSFET is fully turned off, and the RDS on reaches its maximum value. At the bottom left of your screen, you can see a classic half-bridge silicon carbide MOSFET gate driver configuration, where, as we discussed previously, the gate driver is responsible for driving the gate to source voltage, or VGS, from low to high for turn on and high to low for turn off. The gate driver current can be approximated as the QG total divided by the on-off time, where the total gate charge, or QG total, is the amount of charge in coulombs that needs to be injected into the gate electrode to turn on and off the MOSFET fully. On the right, on the right-hand side of the screen, you will see a plot of one of onsemi's 1200-volt, 22 milliohm silicon carbide N-channel MOSFETs, with the gate charge in nanocoulombs on the x-axis and the VGS in voltage on the y-axis. And you will note, for this particular silicon carbide MOSFET, the VGS range is 21 volts, from -3 volts to 18 volts. Now the VTH, or the turn-on threshold, is 2.72 volts at 25 degrees C at about 18 nanocoulombs. The Miller plateau is approximately 7 volts and runs from about 35 nanocoulombs to about 70 nanocoulombs depending on the VDD. And for this M3S family of silicon carbide MOSFET, at a VGS of 18 volts, the QG total is 140 nanocoulombs, yielding the low RDS on of 22 milliohms. Now, if you look back to the left of your screen, I am showing you the typical peak source and sink currents of our flagship silicon carbide gate driver, the NCP 51561, with a 4.5 amp typical source current for turn on and a typical sink current of 9 amps for turn off. So, if you run my first order approximation handy-dandy calculator, you will see for an on time of 33 nanoseconds, assuming 140 nanocoulombs of total gate charge, 4.24 amps of gate drive is recommended. If you recall back at the beginning of this webinar, we said for many of these high-power applications using silicon carbide MOSFETs, we highlighted a market trend towards faster switching speeds, because faster switching speeds can yield higher power densities, or a smaller physical form factor for the same amount of power, or the same physical form factor with more power. Something I have not mentioned is that for some of these high power applications, a common technique is, at a given frequency, to vary the duty cycle or pulse width modulation, or PWM. In this example, I vary the duty cycle, or PWM, from 50% to 10% in 10% steps, where at each step the falling edge moves to the left in time while the rising edge of each period is constant. If we zoom into the 50% duty cycle example, in black you can see the ideal pulse width, but in blue you see the actual pulse width, which can be truncated in time at the maximum VGS due to the slew rate of the on time. As you decrease the duty cycle, depending on the frequency and the on time, if you're not careful, there is a possibility the actual pulse width at the maximum VGS becomes compromised to the point where the maximum VGS pulse is actually swallowed by the on time, resulting in unwanted run pulses. So, the takeaway from this slide is to be mindful of this and size your gate drive current, or your IG, for the worst case switching frequency and pulse width modulation. The large table in the center of your screen captures more detail on how frequency and a worst case 10% duty cycle, or PWM, can compromise the actual pulse width at the maximum VGS. For this discussion, we will start at the highlighted row for 100 kHz switching frequency. The first column to the left captures the pulse width modulation switching frequency, or 100 kHz. The second column captures the corresponding period, or 10 microseconds. And the next 5 columns capture the ideal pulse width from 50% pulse width modulation down to 10% pulse width modulation, where 10% pulse width modulation is highlighted in yellow. The next 3 columns in light red assume a 15 nanosecond on time for a worst case 10% pulse width modulation. The resulting actual pulse width is 985 nanoseconds. If you compare that with the ideal pulse width of 1 microsecond or 1,000 nanoseconds, the final column in light red captures the actual pulse width is 98.5% of ideal. The next 3 columns in light blue capture the same information, now with a 33 nanosecond on time. If we look at the small table on the top right of your screen, you will note a first order approximation gate drive a 9.33 amps source current for 15 nanosecond on time in light red, and 4.24 amps source current for a 33 nanosecond on time, assuming a QG of 140 nanocoulombs. So in summary, assuming 100 kHz switching frequency, 10% worst case duty cycle, and a 33 nanosecond on time, the actual pulse width is estimated to be 96.7% of ideal at the maximum VGS. And assuming a 15 nanosecond on time, the actual pulse width is estimated to be 98.5% of ideal at the maximum VGS. And I will say, I'll close out with this slide. I'll say that for many of these contemporary high power applications, 100 kilohertz is quite fast. But in the future, one can expect switching speeds to increase. And therefore, I wanted to share with you this sanity check so you could have this in your toolbox. I would like to take a moment to summarize some of the efficiency relationships we have discussed thus far in the webinar, recalling what we said earlier, where the total power dissipation is the sum of the conduction losses plus the switching losses. When a SiC MOSFET is fully turned on and the ID current is freely flowing drain to source, as depicted in the block diagram schematic at the top right side of your screen, where the green arrows capture the current flow. In order for efficiency to go up, the designer needs to select a silicon carbide MOSFET switch with lower RDS on, because Ohm's law teaches us that power equals I squared R. And reducing RDS on reduces conduction losses because the silicon carbide MOSFET is in conduction mode. But if you reduce the RDS on of the silicon carbide MOSFET, then the total gate charge of the silicon carbide MOSFET increases because total gate charge is inversely proportionate to the RDS on, not to mention the CISS or input capacitance and the EON and EOF losses, which also go up as the RDS on goes down. So lowering the RDS on indirectly increases switching losses because higher gate charge, input capacitance, EON and EOF losses augment the switching losses. If the total gate charge increases, then you will need to increase the gate drive source and sink currents. We discussed that earlier. And this will reduce the switching losses, but you need to be mindful and manage the EMI and ringing, especially during turn-off. As you can see in the table of the 1200 volt M3S family of EliteSiC real-world examples, as the RDS on goes down, the QG, CISS, or input capacitance, and the EON and EOF losses go up. So this is a basic summary of the efficiency relationships between EliteSiC RDS on and the gate drive source and sink currents. Before we get to the summary table on the next slide, we need to cover safety and galvanic isolation. As a general rule of thumb, for most low-power applications roughly below 2.5 kilowatt, a non-isolated gate driver is acceptable. And for high-power applications greater than roughly 2.5 kilowatt, an isolated gate driver input to output is preferred because it provides isolation between the high voltage domain and the low voltage domain, which provides a significant measure of safety for the user who in mission mode is electrically closer to the low voltage domain than the high voltage domain. Isolation also helps mitigate against unwanted ground loops circulating through both high voltage and low voltage domains. Non-semi gate drivers use galvanic isolation inside the device input to output, much like a transformer. Some customers and applications will draw a different line in the sand for low versus high voltage. As opposed to 2.5 kilowatt, it may be closer to 1 kilowatt or more than 2.5 kilowatt. The point is to be mindful of using isolated gate drivers for user safety against high voltage injury and reducing ground loops. This table on slide 15 is the main takeaway for this webinar. This table is an easy-to-use, first-order approximation of how to pair on-semi gate drivers to our EliteSiC MOSFETs. The V in parentheses in the gate driver product name prefix signifies automotive qualified. The P or D in the product name prefix signifies industrial grade. All the gate drivers and EliteSiC MOSFETs in this table are qualified for both automotive and industrial grade. As you see in the first column on the left, the EliteSiC MOSFET switches are arranged by breakdown voltage ranging from 650 volts all the way to 1700 volts. The next column captures the corresponding RDS on ranges, and the third column captures the packaging. There are a total of 3 single-channel gate driver product options that we recommend pairing with the SiC MOSFETs on the left, broken down by source current and sink current capability. Moving left to right, the NCT V51752 is a 3.75 kilovolt RMS isolated gate driver input to output with 4.5 amps source current, 9 amps sink current capability, a 30 volt output swing offered in an SOIC 8 package. Next, the NCD V5709X family of single channel gate drivers rated for 5 kV RMS input to output galvanic isolation with 6.5 amp source and sink current with 32 volt output swing, also offered in an SOIC 8 package. And last, we have the NCD V5710X family of single channel gate drivers rated for 5 kV RMS input to output galvanic isolation, 7 amp source and sink current with a 32 volt output swing, offered in an SOIC 16 wide body package. Next, we have 2 product family gate driver options that offer 2 channels commonly used for half-bridge applications. First is the NCD V5575XX family of two-channel gate drivers rated for 5 kV RMS input-to-output galvanic isolation, 6.5 amp source and sink current, 20 nanosecond maximum total propagation delay matching, with a 32-volt output swing offered in an SOIC 16 wide-body package. And secondly, we offer the NCP V5156X family of two-channel gate drivers rated for 5 kV RMS input-to-output galvanic isolation, 4.5 amp source current, and 9 amp sink current, with 5 nanosecond maximum total propagation delay matching, a 32-volt output swing, also offered in an SOIC 16 wide-body package. And finally, we have some footnotes that apply to the above gate driver families. Where you see a 1, that means the gate driver family supports external negative bias during turnoff, something we discussed earlier in the webinar, which improves turnoff efficiency as well as helps mitigate accidental turn-on during intended turnoff. Where you see a 2, this signifies that the gate driver supports desat or desaturation, which is an overcurrent protection mechanism in the gate driver. Where you see a 3, this signifies the gate driver family supports the active Miller clamp, which clamps the VGS, preventing accidental turn-on during intended turn-off. Where you see a 4, this signifies if the gate driver family supports the internal negative bias during turn-off. You will note that the NCP V51752 above, the single channel gate driver on the left, is the only gate driver supporting internal negative bias. And this saves on system costs because the system does not have to supply that negative voltage. And as I mentioned earlier, the V in the product family name prefix signifies automotive. Next, we're going to take a closer look at the gate drivers in the table on the previous slide. On this slide, we have a summary of the NCP V51752. It's a 3.7 kilovolt isolated gate driver, single channel, and it's got that embedded negative bias generation. As I mentioned earlier, that saves on system cost because the system doesn't have to provide that negative voltage during turnoff. This device does it autonomously on its own. Here we have a summary of the NCD V5709X family. It's a 5 kV RMS input-to-output galvanic isolation single gate driver with high peak current output of 6.5 amps source and sink. And it also supports the external negative bias turnoff and the active Miller clamp protection. And here we have a summary slide of our NCD V57100 and 101 16-pin wide-body isolated gate driver. This is also a single gate driver. It's got 7 amp peak source current, 7 amp peak sink current with 5 kV RMS galvanic isolation input to output. With also has the DSAT, the active Miller clamp, and the external negative bias turnoff during turnoff, as well as fault notification. And here we have a summary slide of the NCD V575XX family. It's a 5 kV RMS input to output galvanic isolation dual channel gate driver. So you could use this for half bridge applications, which are very common. It has a peak current of 6.5 amps per channel, 32 volt bias voltage on the output side, 1200 volt working voltage, and also has a 20 nanosecond max total propagation delay matching between the two outputs. And this is a summary slide of our NCP V51561. It's a 5 kV isolated high-speed dual gate driver for MOSFETs and Silicon Carbide. And it's got a 4.5 amp source current, 9 amp sink current, 1200 volt working voltage with a match propagation delay max of 5 nanoseconds with also programmable dead time control. Sorry about the eye chart here, and this is a table that covers all of our isolated gate drivers that could be used for silicon carbide. And everything that you see in orange highlight, that signifies what the families of gate drivers I put in the table on slide 15, just as a reference. And it gives you more detail with the different columns, some of the features and attributes of these gate drivers. Okay, so more eye charts for you. This slide 23 and the next slide captures more detail of our EliteSiC family of silicon carbide MOSFETs. And you can see by each column, moving left to right, you've got the item number, the product group, and then the family, the breakdown voltage, moving left to right, the ID max, the RDS on typical, the QG total, the VGS range. Keep going, just gives you more information about our parts. And I think this ends just where we begin with 1200. It's sorted by breakdown voltage, and it ends just as we cross from 900 volts to 1200 volts. And this slide just picks up after the previous slide where we're moving on. We're continuing with the 1200 volts and then following up with the 1700 volt EliteSiC products, highlighting in orange, I guess, is the RDS on range of 25 degrees C, and in gray the VAGS operating range, and then finally in light green is the VGS swing. So more information all the way to the far right of the packaging, and then to the left of that is the maximum junction temperature. More information on our silicon carbide switches. Okay, next we're going to look at some application block diagrams using our EliteSiC with gate drivers. This includes a 3 kilowatt power supply followed by a 7.2 kilowatt onboard charger or OBC, then a 5 kilowatt to 12 kilowatt brushless DC motor, and then we'll wrap it up with a 25 kilowatt EV charger. Okay, so this is a block diagram of a 3 kilowatt power supply. Some of the applications are energy infrastructure, energy storage, charging lithium ion up to 15S in series, robotics, industrial drives and pumps, power supplies. And so for the far left, you see an AC input of 85 to 264 volts. And the far right, you see the DC output, which is adjustable. Right here, it's set up from 48 volts to 62.5 amps to 54 volts, 55.5 amps. So moving back to the left, you can see everything in orange is on semi products. You can see the NCP1681 totem pole PFC controller. With the totem pole PFC architecture, you can jettison the full wave rectifier, which is cool. And what you're left with is a slow leg and fast leg totem pole configuration. The slow leg is silicon junction products, and the fast leg we're using in this case are some of our EliteSiC products. And then we're using a 5 kV isolated gate driver for the fast leg, and then a non-isolated silicon junction gate driver, the FAN 7191. And then moving over to the right, you can see the LLC transformer with the integrated inductor, with the LR. And what we have on the secondary side is an NCP 4390. That's our LLC controller that resides in the secondary side. It drives the primary side half bridge through an NCP 5156X or an NCD 5575XX isolated gate driver, and we're driving SiC there as well. And then on the far right, on the secondary side, we've got a half bridge with our silicon junction FETs, and then we're driving those with our NCP 81075 non-isolated gate drivers. And here we have a block diagram example of a 7.2 kilowatt onboard charger or power supply to be used for, well, just what I said, EV charging, an OBC or onboard charger, level 1 to level 2, or as a regular power supply with peak efficiencies of 95.7% at 230 volt, a 320 volt output, or 95% at 400 volt output. On the far left, you can see we've got an AC input of 85 to 264 volts AC, and we replaced our totem pole PFC with a three-phase interlead PFC controller and power factor correction, and that's the FAN 9673Q, and we're using EliteSiC MOSFETs there. As you can see, we're driving those with the NCV 51705 gate drivers. And then we've got our friend, the NCV 4390 LLC controller sitting in the secondary side, driving a full bridge on the primary side for the LLC and a full bridge on the secondary side. And here we have a block diagram example of a 650 volt brushless DC motor from 5 kilowatt up to 12 kilowatt. This can be used for compressors, pumps, robotics, or industrial drives. Assuming a DC rail up to 650 volts coming in gray, you can see the controller on the left. And on the far right in gray, you've got your BLDC or brushless DC motor with the three windings, the U, V, and W windings, where you have, in this case, Hall effect that's informing the controller on the far left, the MCU, or the processor, where the rotor is in its spin. And so that drives, so the controller drives the pulse width modulation into these gate drivers, these isolated gate drivers. And we have three gate drivers, three half-bridge gate drivers, each one of those driving a high side, low side switch for each winding. So we have a high side, low side switch, and we're using EliteSiC for that in this case. So we have a high side, low side switch for the U winding, a high side, low side switch for the V winding, a high side, low side switch for the W winding. So a total of 6 switches. And then we also have current sensing feedback, as you can see here with the NCS 232 DMR2Gs. And those are integrated current sense devices, which informs the controller of the current on each winding as it's going through its commutation sequencing. So this can be doing trapezoidal, sinusoidal, FOC, or other types of commutation. And here we have a block diagram, a very high level block diagram of our 25 kilowatt bidirectional fast charger. This application is a DC fast charging, including level 3, and ultra fast charging level 3, and also V to G or vehicle to grid because it's bidirectional. So you have the 6-pack boost active front end PFC on the left and the dual active grid DC to DC on the right. Again, it's bidirectional, and it uses a number of isolated gate drivers and silicon carbide throughout the topologies, both on the left and the right side. Peak efficiency is 98% at an 800 volt D out for your larger battery, automotive EV batteries. And this is also stackable, so you can have a much larger charger by stacking these 25 kilowatt bricks, if you will. Thank you.